Potential energy move from high to low potential energy. The units used in potential energy is joule. Electric potential energy is about conservation of energy, and it is a scalar unit. Potential energy can be converted to kinetic energy. So the formula used is delta U equals to final potential energy minus the initial potential energy. And also it can relate with the work done, where you use Q as the electric charge and ED is the potential energy. Next, the electric potential V. Electric potential is a scalar unit and use voltage as the unit. The formula used for electric potential is V equals to KQ over R. K is the constant, which is 9 times 10 to the power of negative 9. Q is the charge, and R is the distance between the point. 1 volt equals to 1 joule per coulomb, and electric potential is to measure of how much work do on a charge. The electric potential V also can define as ED. It is also can relate with potential energy and Q using the volt.
Next, I will explain about the potential difference. The potential difference is the difference in electric potentials between 2 points in electric field. So, the first we need to know is the unit for potential difference is delta V, that refer as a voltage. And 1 voltage is equal to 1 joule per coulomb. So, the formula used for this potential difference is delta V is equal to VB minus VA, where V we can get formula from V is equal to KQ over R. So the secondly, potential difference is depend on other charge that create the fields. And lastly, the equipotential surface is directed from the high potential to low potential. So this I will explain more on the next slide. So next, this diagram shows what equipotential surface look like. We can see that the bold pink line is the electric field line, and the dotted green line is the equipotential surface. Equipotential surface is a surface which have the same electrostatic potential at every point on it. This means that at every point on the equipotential surface, a charge will be the same potential energy. Hence, the equipotential surface is always perpendicular to the electric field line, because if it were not perpendicular, then there would be some component of the electric field along the equipotential surface, and some work must be done against that field component. If we wanted to move a charge around on the surface, and that would give rise to a potential difference between any 2 points on the surface, because W is equal to negative. W is equal to Q delta V. Next, we move to the next slide. This picture shows the point charge equipotential surface. The red arrow show out from the dot means this is a positive charge, and the dotted green line is equipotential surface. So as I see here, there are different voltage value, which is 10 volt, 20 volt and 30. So from here we can know which is equipotential surface will be the high voltage. The equipotential surface that nearer the charge will be the higher voltage. This is because like we know, charge repel each other, so it takes more and more energy to move the charge together the closer you get. Therefore, it increases as the potential surface get closer to the charge. Next, the example of potential difference. So this is a cathode ray tube. A cathode ray tube is a vacuum tube containing one or more electron guns which emit electron beams that are manipulated to display image on a phosphorescent screen. So, how the cathode ray tube works? This works when the electricity produced will passes from the cathode to the anode. Then anode will accelerate the electron. Then a small bit of electricity passes through the hole in the anode, and the image are produced when an electron beam strikes a phosphorescent surface. So that is how image has been produced. So other example for potential difference is that the first picture shown is oscilloscope display, where it shows a graph of an electrical signal. This oscilloscope always used in the hospital. So this device can determine the time and voltage value of the signal. How it works? It works when the electron beam can be deflected by uniform electric fields between the deflection plates before hitting the phosphor screen. Then these electric fields are produced by applying a voltage signal to the inputs of the oscilloscope. Then the second picture is a television. This device has a large cathode ray tube as their display. So as I mentioned before, I also explained about the cathode ray tube. So how image can appear on the TV. All image that have been created on the screen appear when the charged particles was accelerating using an electric field. So when the charge hit the screen, they will cause the phosphorescent coating to glow and appear image. So that's how the image will appear on the television.
Let's go to the first question. Three charged particles Q1, Q2 and Q3 are placed at three corners of a square as shown in figure 1. Each side of the square is 0.9 cm. So calculate the force experienced by charge Q3. So first of all, draw a square that has Q1, Q2, Q3 and point A on each corner of the square. Next, draw the vector diagram of Q3 towards Q1 and also Q3 towards Q2. Since Q3 is a positive charge and Q1 is also a positive charge, so it will repel to the right side, while Q3 towards Q2, Q3 is a positive charge and Q2 is a negative charge, so it will attract to downward. So the vector diagram will be like this. Next, we must calculate the force from Q3 to Q1 and also Q3 to Q2 by using the formula F equals to K times Q over R squared, which both of the Q are in modulus. Next, we will insert all the values into the formula, which is K is equals to 9 times 10 to the power of 9 because K is a constant. Q3 is 0.6 times 10 to the power of negative 6 because the charge is in microcoulomb, so we must times with 10 to the power of negative 6. Same goes with charge Q on Q1, which is 0.7 times 10 to the power of negative 6 and divided by the radius to the power of 2. So the radius is 0.9 centimeter, but we must convert
the radius into meter. So it will be 0.009 meter to the power of 2. Next, calculate the force from Q3 to Q2. Same with the previous one, which is we will be using the formula of K times Q over R squared, which is both of the Q will be modulus. After that, we will insert all the values into the formula, which is K is equals to 9 times 10 to the power of 9 times with 0.6 times 10 to the power of negative 6 for charge Q, and don't forget to times with 10 to the power of negative 6 because all the charges is in microcoulomb, so we must convert into coulombs, and times with 0.9 times 10 to the power of negative 6 for charge 2 over 0.009 meter to the power of 2. Since F31 is on x-axis and F32 is on y-axis, so the value that we get for F31, which is 46.67 Newton, is Fx, while 16 Newton for F32 is Fy. So the last step for this question is we must find the magnitude of the resultant by using the formula F equals to square root of Fx to the power of 2 plus Fy to the power of 2, which is, then we will get 76.014 Newton. So let's move on to the next question, which is calculate the potential at point A. To find the potential, we must use the formula V equals to KQ over R. Do not use the formula K times modulus Q over R squared. This is because the formula is used to find force on me. So, because we have 3 charge, so we must plus each charge, which is V total is equals to V1 plus V2 plus V3. Then use the formula of K times Q over R for Q1, Q2 and also Q3. After that, we will insert all the values into the formula, which is 9 times 10 to the power of 9 times 0.7 times 10 to the power of negative 6, because Q1 is equals to 0.7 microcoulomb over the distance, which is 0.009 meter. Same goes with charge Q2 and also charge Q3. However, for charge Q3, we will use 1.3 times 10 to the power of negative 2 for the distance. After adding V1, V2 and V3, we will get 2.15 times 10 to the power of 5 volt.
For second question, the 2-point charge Q1 is positive 5.4 nanocoulomb and Q2 negative 2.8 nanocoulomb are 0.08 meter apart. Point A is a midway between them. Point B is 0.06 meter from Q1 and 0.05 meter from Q2. Let V equal to 0 and R is infinite. Calculate the potential at point A and point B. First, we calculate electric potential at point A. We use formula V equal to KQ over R, which is K is Coulomb constant, so we will use 9 times 10 power of 9 Coulomb as its value. Q is a charge and R is distance. Mentioned in the question that point A is a midway between Q1 and Q2, which is the distance is 0.04 meter. We just substitute the value that have been given in the question in this formula, which is 9 times 10 power of 9 times 5.4 times 10 power of negative 9 divided by 0.04 meter plus 9 times 10 power of 9 times negative 2.8 times 10 power of negative 9 divided by 0.04 meter. So, the electric potential at point A is 585. Next, To calculate electric potential at point B, we use the same method like point A, which is we substitute the value in the formula KQ over R. So the electric potential at point B is 9 times 10 power of 9 times 5.4 times 10 power of negative 9 divided by 0.06 meter plus 9 times 10 power of 9 times negative 2.8 times 10 power of negative 9 divided by 0.05 meter. So the electric potential at point B is 306 V. Next, the question is, what is the work done to move a charge of 2.5 nanocoulomb from point B to A? So from this question, we can use the formula W equal to negative QED, which is ED is a delta V. This work done is on the system and point B need to be moved to point A. So the charge given in the question is 2.5 nanocoulomb and delta V is a potential difference between point A and point B. Substitute the value, which is negative 2.5 times 10 power of negative 9 times 279 V, and the answer for the work done is negative 6.975 times 10 power of negative 7 joule.
The last question for example 2, what is the potential difference between A and B? The question wants to know the difference between A and B. So it doesn't matter if you want to do B minus A or A minus B. So I will choose 585 minus 306 and we will get 279 voltage.